Welcome to Office Hour 5. Again, as usual, I'm going to just say a few things. Just a reminder, we try to have a regular schedule. Workshops due on Tuesday nights. Usually that's the first one on the material. The Pearson homework used to be on Sundays, but I've changed the past few for Wednesdays. The follow-ups are on Saturdays, so you might want to be careful about waiting too long because sometimes they may go down for maintenance on Saturday. So try to do them a little earlier if you can. And the quizzes, which should add up to 100 points, are generally due on Fridays. And so this week is all about Chapter 7. And so I'm going to say a few things about that. One thing is you really need to understand why conversion factors are so useful, because it starts off with basically talking about what's in a formula. What's in a formula, a molecular formula, or an ionic compound's empirical formula, is the ratio, number ratio, of each element in the compound. So for example, methane is CH4. And the conversion factor is that there's 4 hydrogens for every 1 carbon or for every 1 molecule. And so those conversion factors come from within the chemical formula itself. Then it talks about balancing chemical reactions, which is actually a fairly simple sort of thing to do, as long as you realize you cannot change the formulas of the compound. Methane is always CH4. Don't change any of the subscripts to make things balance. You can only change the numbers out front. And so methane requires 2 oxygen molecules to completely burn to carbon dioxide and 2 water molecules. And you get a lot of heat from that. That's why we burn natural gas in the winter. But this balanced equation says on a number basis we need twice as much of these diatomic oxygen molecules as we do methane. So you have to make sure that your furnace is tuned properly, has plenty of air. Otherwise, you won't get complete combustion and you get carbon monoxide poisoning. So the conversion factors here come from the stoichiometric coefficients out front. 1, 2, 1, and 2. Remember, we don't write the ones. So for example, if somebody wanted to know how many water molecules do you get when you burn the methane, well, instead of trying to figure it out, you take the balanced reaction and say, okay, 1 of these is equivalent to 2 of these, no matter what scale it is. So the ratio could be 100 to 200, or 1 million to 2 million, or 1 molecule to 2 molecules, or 1 mole to 2 moles. And that's kind of a special sort of number. What we did for the mole is say, okay, if you look at the periodic table, the atomic weight of carbon is 12.01. And so we decided, okay, let's weigh out 12.01 grams of carbon and kind of count the atoms that are in there and call that number the mole. And so we could have done oxygen in the periodic table. You look at its atomic weight, 15.994, and then if you weigh it out that much and count the atoms, you get exactly the same number, which is called Avogadro's number. And so that's another type of conversion factor. Now this conversion factor is necessary when we change the chemical formula from one thing to another. So a lot of the problems have reactants, which are some molecules, and products, which are different molecules. And you want to know, if I start with so much of this, how much of that will I make? Or if I want to make this much, how much should I start with here? And in order to do that on a number basis, you might have to convert the mass in grams to moles, and you have to use the molar mass for that. And so the molar mass is pretty simple to calculate. You just add up all the masses of all the atoms that make up the compound, and that's the molar mass. So grams per mole is going to be for whatever substance it is. So for example, if I wanted to know grams of methane per moles of methane, well, that turns out to be the mass of 1 carbon and 4 hydrogens, which is about 16 grams per 1 mole. If I want to know about what's the molar mass of molecular oxygen, O2, well, that's 32 grams per 1 mole of O2. And then the last part of the chapter discusses some more sophisticated concepts. So for example, if you burn natural gas in your house, you want to use way more than twice as much oxygen to ensure that you burn it completely and you don't have any carbon monoxide poisoning your house. And so in that case, to make sure we use up all the methane, we make sure we have lots of extra O2. So this concept is called limiting reactant. And then, of course, the one that you have left over is called the excess reactant. And so an example would be hot dogs. And so if you buy a package of hot dog buns, they always come as 8. And the cheap hot dogs that are pink, they usually come as a package of 10. So you know how many hot dogs you can make. When you say a hot dog is a bun plus a wiener, you say, okay, I can get 8 hot dogs out of that, and then I'll have 2 wieners left over. Okay? And so not only can you figure out how much you should get, but how much you should have left over, whatever reactant that you don't run out of. All right, so let's say we do that, and somehow we wind up with 7 hot dogs. So what could have happened? Well, my dog could have happened. My dog is part wiener dog, as a matter of fact, and probably ate one of these. So the percent yield would be, okay, you can calculate how much hot dogs you can get from 8 buns. That's 8 hot dogs. You can calculate how many hot dogs you can get from 10 wieners. That's 10 hot dogs. Well, the amount you expect is the one from the limiting reactant, which is 8 hot dogs. Then you can take the amount you actually finished with, got, and divide by the amount you expected, and that's called percent yield. So in this example, I expected 8 and I got 7, so that's 7/8 or 83%. Okay, I'm willing to take questions now from the audience. That was the question about the workshop grades. Let me check and see. Redox. Okay, well, I can explain redox. It's pretty simple. I'll give you an example. Okay, I mean, that's fine. So that's due tomorrow night. So if you don't understand it, you don't understand. So it's type of reaction. Okay, so the type of reaction is called reduction and oxidation. And like the Frank Sinatra song, Love and Marriage, you can't have one without the other. Although this is definitely always true. The other was a joke. But it's called redox for this reason. And so reduction is gaining electrons. So there's a mnemonic. Oil rig. Reduction is gaining electrons. Okay, so remember we first learned about atoms, said the same number of electrons as protons? And then we learned about ions, which is not the same number. So what happens when you go from an atom to an ion, you lose electrons or you gain electrons. So if you gain electrons, that's called reduction. So that's, if you go from the element to anion, that's, that element has been reduced. The other process is oxidation, and it's losing electrons. So all the elements which form cations, from their element, they get oxidized, and they lose some electrons until they, and so that's really all there is to reduction oxidation. So as an example, all combination reactions. So let's, first of all, we've got to balance this thing. This is iron 3 oxide. That 3 oxygens and 2 oxygens. So this could be 3 halves and 2. But when you do that, you say, okay, the easiest way to balance is now multiply everything by 2. So 4 iron plus 3 O2s goes to 2 Fe2O3 molecules. And then when I look at the charge of oxide, it's -2. When I look at the iron charge, it's +3. That's why it's called iron 3. So the iron had a charge of 0, goes to a charge of +3. It's oxidized. Iron is oxidized. So you might see sometimes a 0 for the charge of an element above it, and that's somehow to indicate maybe there's some important oxidation states of that element that occur, like iron. So iron goes from 0 to 3, so it lost 3 electrons. That's oxidation. And see, there's something called the oxidation number, which is basically the charge on the atom. And if that goes up, that's oxidation. And if it goes down, it's reduction. Okay, if there's any further questions or follow-ups, that'd be fine. What's the next question? Well, you get, if you add up the quizzes and it's more than 100, boy, you get lucky. It's only based on the number of points. So it won't be exactly 100. It's pretty close. Okay, none are showing up. Well, it's a good question about redox. It's really kind of like a one-off thing in the text. So I don't really see too often anywhere else where it really comes into play, where they actually use the concept that much. It might be more important when they talk about the biology example of FAD and FADH2 and what that means. So if you take biology class and then you learn about oxidation and reduction as far as these molecules are concerned that add or remove hydrogen atoms and electrons at the same time. Might see me at UAB night. I'm going to the baseball game, the Barons game tomorrow night for 50-cent hot dogs.